Good morning. I'm Bradley Miller. Welcome to this news briefing from the 253rd National Meeting and Exposition of the American Chemical Society in San Francisco. We're joined today by Dr. Chao Wang from the University of California, Riverside. He'll be talking to us about his work on new materials that could lead to self-healing smartphones. Dr. Wang?
Yes, thank you, Brad. And actually in our group, we have developed a type of self-healing, transparent, and stretchable ionic conductor. This material has many very interesting properties. First, it has very good ion conductivity, so it can be used in a number of applications, including sensor, artificial muscle, and energy storage. At the same time, different from conventional ionic conductor, is highly stretchable. It can be stretched to 50 times of its original length. At the same time, it's able to self-heal at room temperature. What's more, and it's highly transparent. And using this great material, and we have shown an example of using this material to demonstrate a self-healable artificial muscle. But this type of material, and we develop is through we develop a new type of interaction using the ion-dipole interaction to develop this type of new self-healing materials. We expect that this kind of material will have a number of applications and in the area of, as I said, sensor and also energy storage and artificial muscles. Yeah.
Are there any questions? Please state your name and affiliation before asking.
Kath O'Driscoll from Chemistry and Industry magazine. Mm-hmm. Can you say something about the cost of this new polymer and what other polymers will it actually replace?
Okay, and yes, so the question is about what's the cost of the polymer, and I cannot say the exact cost of this polymer, but I can definitely say that it's low cost because this polymer itself and most of the components are actually from commercially available materials, so they are actually very low cost, and especially when they scale up, the cost will be even lower. Yeah. And also about the polymer, what they will replace. I have to say that this material will be a totally new material. It will generate new properties for the devices and for the new applications. I don't think any material can compete with our material to say exact competence with our material right now. Yeah.
You mentioned that one of the problems in the past has been with the performance in high humidity. How are you addressing that problem? Yeah, and
I think from the self-healing design, I think for the humidity would be one of the issue in the past because the self-healing materials are can be affected by the humidities because a lot of them using the hydrogen bonds or using some bonds including type of metal coordination bonds. They could potentially interact with water and then make the mechanical property drop within the high humidity. But here and in this material, we haven't demonstrated that very good yet. But in our next work, we would like to present our the self-healing material under harsh conditions. The secret is that we are trying to make the whole system as hydrophobic as possible. In this way, and the whole polymer itself, it would be very hydrophobic, and then it will not have any affections with this type of materials, yeah, with the water. Mm-hmm.
Sam Lemonek, I'm freelance. Can you talk more about the properties, the physical properties of the material after it heals? Does it retain all of the properties of the original uncut material?
Yeah, and you mean you want to know the property of material or the recovery of the materials? I think for the material, and it's pretty like a conventional soft rubber, and depend on the composition of the material and the stretchability could, the Young's module could be around 1 megapascal, and the stretchability could be 500%, and 5,000%, yeah, of the original length. And regarding the recovery of the material, when you cut it and put it together, within 48 hours, it can recover all its mechanical properties, including Young's modulus, including the ion conductivity, including the stretchability. So it's fully recovery, and nothing has happened before. Yeah.
We have an online question from Christine Suh, American Chemical Society. She's asking, does pressure have to be applied for the two pieces of the material to reconnect?
Yeah, that's a very good question. I mean, right now, because what we do is actually extremely cutting case, which means that we have a piece of material, we cut completely into two pieces. Then we have to put it together, yeah. And here, actually, we just use a gentle kind of like a press to put them together. But, it's not a high pressure. But right now, we are also like study what would be the pressure like influence on the self-healing of the materials. But here, the gentle pressure is just to make the material can get in touch with each other. It's not like used to heal the materials. But I think it's definitely right, and we need to make a more systematic study. And when we do this type of operation, and how can we study the different pressure and affecting the self-healing efficiency? Yeah.
Ben Valsler, Chemistry World. I'm just wondering about this polymer's other properties. So it's a conducting polymer. Is it a very good conductor? Is it good enough to be used in the sorts of electronics we currently have?
Here is not like an electronic conductor, it's an ionic conductor.
Right.
In the past, I've already published a paper of a self-healing electronic conductor, and it was published like in 2012. And this one is an ionic conductor. And your question is about application, right? Yeah, I think this will be very like promising for a number of applications because its ion conductivity is 10 to minus 4 Siemens per centimeter. It's not a very, it's pretty decent ion conductivity for a number of applications, including the electronics and artificial muscle. Here, actually, in our paper on advanced materials in 2017, and we demonstrate that this type of material can make a transparent artificial muscle. Yeah.
So the other thing the press release mentions is potentially self-healing lithium-ion batteries, which are of great interest for a whole host of reasons.
Yeah.
How do you see that work developing?
In fact, I published a paper in 2013, and we do have a self-healing like a battery, and it's used to solve the problem of a silicon anode because silicon is a type of high-capacity electrode materials, and which would be very promising for the next generation of batteries. But the problem is that during the lithiation of the silicon, and it will cause a huge volume expansion and making the material just broke into parts. But we use a self-healing approach to make it able to self-heal at the same time. And then we can tremendously increase the performance of the silicon anodes. And again, so come back to this work, I think this property, combining the self-healing and also the high conductivity and ion conductivity and also the stretchability, definitely will make a lot of sense to improve the performance of lithium-ion batteries. That's also one of the directions we are working on right now. Hopefully, it will come out as soon as possible. Yeah.
Okay, we have an online question from Hania Ray for PC Magazine. When would a phone like this be a commercial product, or a phone that integrates this material be a commercial product? What challenges do you have before that's possible?
I think right now, and for cell phones, there are already self-healing materials, in LG cell phones, and actually the back share is made of self-healing materials. When you have a scratch on it, and it will recover within 1 day or 2 days. So that's already the very first material that introduced into smartphones. And but that material has no electronic properties. It's just mechanically a protector over there. And about our materials, I think when we want to bring it to the real cell phone, I think we still have a lot of challenges to conquer, and including the reliability, and also the operation at different conditions, in cell phones, different temperature, and also different conditions, high humidity or different things. I think we still have a lot of things to do, and before we can really use it for smartphones. Yeah. Yep.
Sam Lemonek again. Have you explored at all the biocompatibility of the polymer? Is it possible it could be used for a wearable or an implantable device?
Yeah, that's a very good question. And right now, I think from my limited understanding about this material, I think right now it's not a good time to say that it's biocompatible. But definitely that would be a direction to make it to be biocompatible materials, wearable, really wearable, can get in touch with the human or even implant into human beings. But at this stage, I think this material design is purely for devices, not really for biomedical devices. But definitely that would be a trend, like to make materials that could be higher biocompatibility to explore like a wider applications in these areas. Yep.
Thank you very much. The archived version of this session will soon be placed at bit.ly/ACS-live_San Francisco. Please join us for our next press conference today at 10:30 a.m. Pacific Time about progress toward stopping the Zika virus from crossing the placenta. Thank you for your time today.